Any questions before we get going? Today we're going to cover something that's a little complicated, and some of you are going to be a little stressed by it. This is going to be oblique incidence. Now, here's the deal. Do you remember I said normal incidence is when the wave comes in and it's perpendicular to the surface? Both E and H are in the plane of the intersecting surfaces. Do y'all follow me? Now we're going to do oblique incidence. So that means if this is the electric field, it could be propagating like this and hit this boundary, and some reflects off, some transmit. Y'all follow me in this class? Now please, I'm going to slow down, but pay careful attention to this. I'm not going to expect you to remember the complicated formulas, but you have to understand the theory, at least in principle. So here's what we're going to do. We're going to have two regions, region 1 and region 2, all right? I'm going to try to be as consistent with Wentworth's notation as possible. I'm not a fan of some of this stuff, but you know, everybody's got their reasons for it. So that's going to be the Z direction. Now here's the deal. The electric field is going to be coming in at an angle. The way Dr. Wentworth defines this is some angle theta incident. Y'all follow me? And the electric field is going to be sticking out of the board. So that's the electric field, and the magnetic field will be in the plane of the board. Now, let me explain this. Do you remember I said that if I have E crossed H is the direction of propagation? How many remember that? All right. So if the E field's sticking out of the board and it's propagating this way, then H has to be in the plane of the board. You all see that? E sticking out, crossed in H is the direction. It's propagating this way. And if that's E, then H has to be in this direction. Do y'all follow me? Everybody? This is in your book. It's called oblique incidence. This would be the incident field, right? Now there's some angle in theta incidence. Now there's going to be a transmitted field, and that means there's going to be something transmitted here. The E field will still be out of the board. It'll be called E transmitted. The H field will be in the plane of the board. Y'all follow me? This isn't hard right now, but you have to see what's going on. I got an E field sticking out. It comes in. It hits. Some of it's transmitted. There's an angle called theta transmitted right here, right? Y'all follow me? Now, how many played billiards in here? Pool, whatever you want to call it. Right? When a ball hits, it reflects off at the same angle it comes into if you have a normal. Y'all remember that? I mean, unless you put English on. Same deal here. I'll prove it in a second. But there's also going to be a reflected field, and I kind of spoiled it for the Dr. Wentworth's book, because the actual electric field will be, reflected field is coming out of the board, but there's going to be an H field. Now, E cross H is the direction of propagation, so there's an H field reflected like this, too. Y'all follow me? And by the way, there's an angle here, theta reflection. And I'm going to spoil it for everybody. Theta reflection equals theta incident. We'll prove that, but I just want to put this up there. Y'all follow me, class? So far, I've just defined a transmitted reflected field from an incident set of fields. Now we need to mathematically define this, and here's where it gets a little interesting. This is going to be the x-axis, because this is going to be a right-hand coordinate system. So I know x crossed y would be out of the board. You all see that? And z and x are in the plane of the board. With me? Now I need to mathematically define the incident field. Here's where it gets a little more difficult to understand. All right, I'm going to expand this a little, so you can see this. Let's take this point where the incident field's coming in. This is theta incident, right? I want you to look at something. The direction it's propagating, if that's theta incident, this is the electric field coming out, is this direction, right? Y'all follow me? Correct, class? Now, that direction becomes very important to define carefully, as well as this distance. You see how it's moving in this direction, and we know it's going to bend right here. Well, what we want to do is talk about some distance, and they call it, in Dr. Wentworth's book, Z prime. That's going to be a distance measured on this axis. It gets a little hairy here, so just follow me. Y'all with me? I mean, if we're measuring this way, we could say 1 meter in the x. If we're measuring this way, 1 meter in the z, 1 meter in the x. But we could say the wave traveled 1 meter on this axis. We'll call it the z prime axis, okay? Now, what is z prime? Just listen to me and you'll see it.
You're good. You're good.
We know this would be z, and this would be the distance x traveled. Do you all follow me? I'm trying to make a right triangle there. Follow me? Now, the projection, if I take right here z times the cosine of theta incident, I would get this distance from here to here. Do you all see that, class? And if I take x times the sine of theta incidence, I would get the remainder. That's not actually showing up very well. Right here, if this is x, this distance from here to here would be x, or sorry, make it z. Pardon. This would be z cosine theta incidence, and this, if this is theta incidence, and this distance from here to here would be x times the sine of theta incidence. Does that make a little more sense? Can you all see that? So the total distance z, if I'm calling this some z prime right here, z prime, write this down. You can look at this later, but this is the best way I know how to explain it. That's z prime. If you have any given distance here, there's going to be a component that has an x. If you took a projection in the x direction, you would have that. And if you took the projection in the z direction, you'd have that. Do y'all follow me? Class, are you with me on this? I mean, just think about it. If you have this, and I take the projection on the x-axis here, it would be what? The sine of this angle times the hypotenuse would be this, right? You all see it? If we wanted this projection, it would be what? The cosine of the hypotenuse times that. Y'all follow me, class? What I'm trying to just show you is, really, this can be defined in terms of x and z as long as the angle is accounted for. This becomes critical. And you can see in the limit, let me put it down and you'll see it. So this is really z prime is equal to z cosine of theta incidence plus x times the sine of theta incidence. And the way you always check this is do it in the limit. What happens if the angle here, all right, goes to 0? Then z should become z prime, right? Does it? Well, when theta is 0, the cosine of 0 is 1, and the sine is 0, z prime becomes z. Do you all follow me, class? Then do the opposite limit. Now pretend it's going straight up, all right? Therefore, the angle would be 90 degrees, right? I would have x times the sine of 90 is 1, and the entire z prime axis would just be the x-axis. It would be the x distance traveled. You all follow me on that? Just trying to make sure you see this, because this is the point where people kind of miss it at times. I want to make sure you see that. Now that's z prime, and that is for the incoming wave. There's also a unit vector in the direction it's propagating. Just think about this for a second. If I want a unit vector in the direction of propagation, how would you get it? I mean, intuitively you already know. I know you do. If I make this be 1, right? Then the projection of that hypotenuse in the x direction would be ax, right? And the projection in the ay direction would be the ay component, if you think about it. If I make the hypotenuse 1. Does that make sense? Here, let me just write it down for you and you think about it. That means the unit vector in the direction of propagation for the incident wave would simply be cosine theta incidence a, this would be az actually. No, wait a second. Yeah, az, pardon me. Plus sine of theta incidence ax. And just think about this in the limit too. And I'm going to slow down here and make sure everybody catches this, because this becomes important. Now, when I say unit vector in the direction of propagation, if that angle goes to 0, you see that's normal incidence, right? It better be in the z direction. Do you all see that, class? So go over here. By the way, if you didn't get your home or get your quiz, it's so I don't know. Did you get yours? Is this you?
Yeah.
How do you pronounce your first name?
Abdul Rahman.
I didn't catch it.
I tell you what, see me after class. I'm gonna do this real good. I've been around too many guns and anyway. When it goes this way, I'm not kidding either. I mean, you guys can probably hear great, but firearms just don't help your ears. Anyway, when you're going this way, think about it. If I'm normally incident, it's AZ, right? If theta is 0, look over there. When theta is 0, cosine is 1, right? Sine is 0. Y'all follow me? Now, if it's going straight up, it's all AX, right? Look over there. When theta is equal to 9. Y'all see that, class? So that checks the boxes of confidence. And whenever you're looking at stuff, and I've warned you about this because I've trained myself to do this, don't accept anything as absolute truth in a journal article. You'll be reading journals or anything like that, technical documents. Go and prove it to yourself. There are errors, and I mean there are errors in papers in Nature. The very first paper I ever published is Nature. It's grueling. They have 5 reviewers. They absolutely clobber you. But they try to eliminate the problems with notational things that aren't correct, something like this, any kind of inaccuracy. The problem is, if you're a human being, you're going to make an error. And sometimes those errors cost a lot of money. So don't take anything on just absolute faith until you prove it to yourself. That's my one warning, because I've been burned doing that many times. All right. Now, how do we define this electric field component in terms of this notation? Do y'all follow me? Here's how we do it. I'm going to do it right here. And I know I can't move past this line of death.
Okay.
So, when I do this, my electric field, remember, I said it's sticking out of the board, right? Any idea what we call this form of polarization? There's 2 forms you can have, perpendicular or you can have parallel. Think of this. You see how the E field is perpendicular to the plane it's traveling in? That's perpendicular or transverse electric polarization. So here, we're going to be talking about field quantities that are transverse electric. And it's also called perpendicular polarization, or TE, transverse electric, and the symbol a lot of times is that. All these things mean the same. TE, perpendicular, or that symbol that looks like a perpendicular. Y'all follow me? They all mean perpendicular polarization. The E field sticking out of the plane of propagation. One other thing I'm going to tell you, this is another way to think about it, because you're going to see that you'll see people saying it's TE, it's a TE wave, and you're going to wonder, how do they know that? You see how when this wave is incident, here's the interface, right, between the regions? Do you see how the E field is completely tangent to both regions? You see that? It's right in the plane that intersects this, right? Now the H field is this way. The H field, it has a component that's in the plane, but it also has a component normal to the plane. Y'all see that, class? And that's why this is called TE polarization. The E field's perpendicular to this plane it's traveling in. It's also right stuck square into the plane that it intersects between the 2 regions. I hope that makes sense. So how do we notate it? And this is consistent with Wentworth's book. You're always going to have some scalar magnitude, E naught incident. I'm going to do this in the phasor domain. Then you're going to have E, and now minus J beta 1. Beta 1 would be the beta in this region. It's going to have some beta 1, some eta 1. Now, instead of putting a Z there, we have to put Z prime. Y'all follow me? I'm going to expand Z prime here. I don't usually do this. This is going to be equal to X times the sine of theta incident plus Z times the cosine of theta incident, and it is in the AX direction. Do y'all follow me? Now that's the electric field incident in terms of the way we're notating it. And you shouldn't make it, see that Z prime there? Typically I just write Z prime there, but the first time I'm going to write the entire thing. You with me?
Why is the E field in the X direction?
Oh, AY, pardon me.
Okay.
That's on me. And this is in his book. I want to give you a reference point. If you have your books and you want to know where I'm coming from. Thank you very much. it has to be perpendicular to the board again. This is T polarization on page 360, and he shows 361 is the diagram I'm trying to show. So you can put that down. All right, that's the incident electric field. Now, the transmitted electric field, all right, this is going to be transmitted. There will be some E naught transmitted that we're going to calculate. Then it's going to have the same exact form as this, except beta will become beta 2, because it's in region 2. And instead of theta incident, will be theta transmitted. So here we're going to have some beta 2 and some eta 2. That E naught is just a scalar constant. It's going to be times e to the minus j beta 2. And it would be just like the z before, only now we're going to have x times the sine of theta transmitted plus z times the cosine of theta transmitted. And this is going to be in the a, y direction as well. It's coming out of the board. You with me? Those two kind of check boxes, they make sense. They're really similar, right? In every way, except that the coefficient is beta 2 and the angle is the transmitted angle, correct? Now, the third one is a little different because now we're talking about the reflected field. You'll notice the reflected field is moving that way, right? Correct, class? Now here's the deal. For the reflected field, you'll have some scalar value, E naught R. Again, it could be 1 volt per meter, it could be 10. We don't know what it is. I'm going to show you how to figure that out. Then it's going to be E, it's going to be minus J, here it's beta 1. I want you to follow me on this. This is important. You see how when the wave hits and reflects, it's still going in the positive x direction. You all see that? As time goes by, x is increasing, but z is negative. You all see that, class? Now it's going in the negative z direction. The way we account for that, it will have x sine theta, all right, or theta reflected part of it, but they will be the same. But then I'll have minus z here times cosine of theta reflected, a y. Everybody with me on that? And again, this is notation. The real thing about electromagnetics, and in general, engineering, is you have to have exact notation if you want the right answers when you're solving problems. It becomes exceedingly important to do this and being consistent, or else everything falls apart. How many understand at least that notation for the way we're going to do business? And this is consistent with this book. Yeah, did you have, okay, you're good? Now the next thing we have to do is get the H field, right? Do you mind if I erase that drawing right there? We kind of know it's going to be incident, reflected, or transmitted. So give me some board room here. By the way, I don't know what's going to happen with the storm system here. I just heard it might be high winds. I just want to make sure that I didn't hear, you heard something. If you heard something else, let me know. There's no closures, nothing like this. We expect high winds later today and tomorrow, and maybe some rain, but as far as anything severe, anybody live down around New Orleans, Mobile, any coast down there? If you're down, if you need to leave for whatever reason, I understand, to help move and stuff like this, because I've had that happen with hurricanes in the past. Just want to make sure that stays. All right, now we need the H field. These are propagating plane waves, right? So, any takers? Well, if you got a propagating plane wave in the phasor domain, the best way to get H, in my opinion, would be 1 over eta of the region, unit vector in the direction of propagation, crossed into the E field. Remember, I said that way you don't have to do the curls. Y'all remember this class? Curls are a pain, especially in spherical coordinates. Right. So this eliminates that, and we're going to be doing this. We're in Cartesian coordinates. This isn't too bad at all. So first I'm going to get the H incident. Now it's 1 over, this is going to be 1 over eta 1. Let me do this. Let's assume we're in both regions are lossless. Because if they're not lossless, gets a little more hairy, and we don't need that. What we need to do is focus on the essentials right here, okay? So it's 1 over eta. That's going to be a strict real number now that I made losses. Then it's a unit vector in the direction of propagation, right? You may not remember this, but I put it up there. I don't know if I got it up there. So it's going to be what? Cosine theta incident, right, times AZ plus sine of theta incident, it's AX. Do y'all agree with that? And again, I'm just repeating what I've got up there. And if you want to just follow along in your book, it's fine, but I like writing this out and showing people. Now we got to cross it with the E field. What E field? The incident E field. And here I'm going to do something, because now I've written it once. I'm just going to call that E naught incident, right? E to the minus J beta 1. Now I'm going to use the Z prime notation there to save myself a little writing. Okay, class? And it's what? A Y. Correct, class? To be consistent with everything, right? Go ahead. If you got a question, ask. You're probably not the one. Did you have a question, sir, or not?
No.
Okay. I mean, if you got a question, you look cross at me, please ask it. It's probably somebody else's question that didn't ask it. Okay. Don't worry about that. Yeah.
Isn't the magnitude supposed to be 1 of that?
What?
Isn't the magnitude of that vector supposed to be 1 direction?
Yeah, it is.
It's. What do
Pick
you
a
have?
value of theta. Go ahead. What would you like?
30.
30 degrees?
Go for it.
30? Now, what's the cosine of 30? It was what? Square root of 3 over 2. You had to do this. Square root of 3 over 2 is the sine of 30. 1/2, right? Take square root of 3 over 2 squared, add 1/2 squared, take the square root of the whole thing, it's 1.
Gotcha.
Okay. It has to, matter of fact, just do this. Take the square of this, cosine squared, plus the square of this, sine squared. Sine squared plus cosine squared of 1, square root is 1, period. All right? Okay. Back to this thing. And I appreciate your
Acknowledgement.
suspicion. I'd be suspicious. Now, look here. Here's what I'm going to do. First, I'm going to take the constants out in the front. You all see I have 1 over eta and I have eta naught, right? So this is really eta naught over eta 1, right? So I made it lossless. I can take this out front. That's a phasor. It has no vector direction. Beta 1 times Z prime. Now, the rest I have to go through and cross. I have AZ crossed AY, which is minus
Negative X?
AX, right, class? Sure. So that's going to be Y. That's going to be Z crossed Y is minus AX. So it's minus cosine of theta incident AX. And then what do we get here? X crossed Y is Z, and it's positive. So it's plus sine of theta incident AZ. And that would be the H field incident. You see how I got it? Let me see this right here. I'm going to save us some time. You remember how the transmitted field, the transmitted E field, looked just like the incident E field except for beta in the argument, beta 2, and also the angle was theta transmitted, not theta incident, right? I can make the argument because of the similarities and everything, the H field will have the same form I just put up there, only with the transmitted angles in eta 2 and beta 2. You all with me on that? So it'll save me a little time. So when I take a look at H transmitted, it'll be equal to that basic form. It'll be E naught transmitted over eta 2 now. It's going to be E to the minus J beta 2. Now here's where, I call it beta 2. Here's where I have to be careful. I call this Z prime, right? I'm going to use Z transmitted here to be equal to, here it's going to be Z times the cosine of theta transmitted plus X times the sine of theta transmitted, right? That will be my new direction, I mean linear direction is propagating it. And then there'll also be an A propagation of the transmitted wave. This is a unit vector in the direction of propagation for the transmitted wave. And it's the same exact form as this, only now transmitted, and the transmitted angle has to be put in there. So I take, to get this, it's gonna be this, and well, I'll just do it. When I do the cross product, I'm gonna get this exact same form. I can put the sign first if you'd like, because I think he does that in the book. Sine of theta transmitted AZ, and it's gonna be minus cosine of theta transmitted AX. And that's it for the transmitted. Agreed, class? You can see that that is nearly identical to this, except theta transmitted replaces theta incident. I moved these around. I've reversed the order. And instead of incident A to 1, I got A to 2, or transmitted A to 2, okay? Now here's the difference. When you take a look at the reflected field, all right, and that'll be, I'm gonna put this over here. Remember, then Z for the reflected field will be, it'll have the form of still X times the sine of theta reflected, but it'll be minus Z times cosine of theta reflected. You all follow me on that? And the reason is it's going in a minus Z direction, isn't it, class? Y'all with me, class? All right, so when I come over here for the reflected field, I have to take the E field that is reflected, which is right there. I'm going to do this one. So it's going to be E naught reflected times E to the minus J beta 1, and I'll put the whole thing in here. This is the hard one. X times sine of theta reflected minus Z times cosine of theta reflected, right there. It's in the AY direction. Wait a second. Let me, I want to do it the right way. 1 over A to 1. Unit vector and direction propagation. This is the thing I wanted to get. Now the vector propagation is going to have a minus in front of that Z. That's the point, right? If this is equal to the actual value of the distance variable, then the unit vector and the direction of propagation for the reflected wave, right here, will be equal to sine of theta reflected AX minus cosine of theta reflected AZ. Y'all follow me on that? Because the wave is going this way, right? It's going in the negative Z direction, positive X. Y'all follow me? So I have to put that in here. So it's sine of theta reflected AX minus cosine of theta reflected AZ, and now it's crossed, that is crossed into the E field. And the E field itself is E naught reflected over A to 1, E to the minus J beta 1, and here I'm getting myself in trouble sticking all these angles in here, but it's going to be X times the sine of theta reflected. If I do it this way. X times the sine of theta reflected minus Z times the cosine of theta reflected. And this is in the AY direction. I'm cramped there, but you follow me, and it's in his book. You with me, class? I just rewrote the notation for the E field. I do the cross product, and for the H reflected, I'll take the scalar values up front. I had that twice, so it's going to be E naught incident, or reflected, pardon me, E naught reflected right here over A to 1. Then we're going to have E to the minus J beta 1 here, X sine of theta reflected, minus Z cosine of theta reflected here. That's all the scalar terms. Then we take 8x crossed AY, we get AZ. So we have sine of theta reflected AZ, and then we have z crossed y right there is minus ax, but it's got a minus sign, so it's actually plus. Plus cosine of theta reflected. And here it's going to be ax. And I want to make a comment here. I'll erase this. But when you're thinking about this, you got an electric field striking that, the electric field's out. Then you got an electric field moving in this direction out of the board. Think about the H field. It has to be E crossed H. H has to be in this direction, doesn't it? Right? Where it has both positive X and Z components. Y'all see that? I'm trying to show you that if E's out of the board, right here, and it's probably getting that way, well, E cross H has to be the direction of propagation, but so the H field looks like this, and it has positive X, positive Z components. Do y'all see that, class? For the reflective wave? People miss that sometimes, and I'm trying to make sure I say it and underscore. So that's the reflective field. Spent a lot of time doing this. This gets, I know, a little irritating because it's a lot of book work. And that's why usually they make notations. They'll call one Z prime incident, then Z prime reflected, then Z prime transmitted, so I don't have to rewrite all this stuff all the time, okay? But anyway, once we have that, here's where it gets interesting. Now we want the transmission and reflection coefficients. With me, class? How did we do it last time? I'll do it. We're right there. Anybody? Remember we had normal incident waves? We wrote an equation for the incident E field and H field, didn't we? And transmit. But then what did we do? There was one cardinal thing, or one key thing we did. Right at the boundary between these two regions, right? If that's region 1, that's region 2, what happens? Remember the tangent E field on one side was the tangent E field on the other? And the tangent H field on one side was the tangent H field on the other. You remember that? E tan 1 is E tan 2. H tan 1 is H tan 2. How many remember that? That was the key that allowed us to get the reflection and transmission coefficients, right? Now what's the value at Z right here? You know it, come on. It's 0, right? I always put the boundary between region 1 and 2 at Z equals 0 to make my life easy. Right? If you're an engineer and you have the option of making your life easy, do it. Right? You'll have enough trouble without adding some to it. I mean, it gets really complicated. So now if we take Z equals 0, here's how we get the boundary conditions. If you look at this as Z equals 0 for the E field, here I got the E field. You'll notice that if Z equals 0, that term goes away, that goes away, and that goes away. And I'm left with this stuff, right? Right, I just have the E to the minus J beta X business. Do y'all see that, class? Now you don't have to write this down, but I want you to follow me. So at Z equals 0, when I take E tan in region 1 equal to E tan in region 2, then I'm going to get E naught incident times E to the minus J beta 1 times X sine of theta incident. That would be this incident field, but in region 1 we have a reflected field at the same point, so we have to add to it E naught reflected, E to the, and now this is going to be, if you look at this, it's going to be minus J beta 1 X times sine of theta reflected, and that has to be equal to E naught transmitted here times E to the minus J, and this will be beta 2 times, I put these here, I probably shouldn't have, beta 2 times X, and this is sine of the transmitted angle. Now here, do y'all follow me on this? The only thing I did is set the electric field in region 1, which is just the incident reflected field, right? They're superimposed at all points, correct, class? This is the phase domain. We're right at Z equals 0, so the Z cosine business goes away. And that has to be equal to the tangent field. Y'all know what I'm saying, what I mean when I say tangent, right? Tangent is going to be something in the plane of intersection. It has no components other than the plane of intersection. Now, y'all see this, class? I want to make a comment here. This is real important. You see it. In order for this to be true, think about it. This e to the minus j, all that junk there, that's an angle, isn't it? It's like e to the j, after all is said and done, it would be like 40 degrees, 5 degrees, right? This is the same angle, isn't it? This has to be the same angle. Here's what I mean. If I have a at e to the j 30 degrees, right there. Let me do it this way. E to the to the j f of x plus b e to the j g of x equals c times e to the j, and I'll call it h of x. The only way this statement can be generally true is if f of x equals g of x equal h of x. The angular functions have to vary at the same rate. If they don't, it won't be equal always. It'll be equal only at a point. Y'all follow me? Just do the math logically and you'll see it. It also means that the magnitude, when you add these two things, all right, have to be equal to c, always. Now, here's the neat thing. This is where Snell's law comes from. When I do that, and I set these exponential values equal to each other, I get this. I get beta 1 right there. And you can forget x, because that's going to cancel when I equate it, but I'll put it down one time. Times the sine of theta incident will be equal to beta 1x times the sine of theta reflected. And it will be equal to beta 2x times the sine of theta transmitted. What I've done here, and I know I'm pushing the limit of what I can do.
You're good.
But what it amounts to is I've equated these exponential arguments, all right? They have to be equal for this to be generally true for all values of x. Do you follow me, class? Now the x goes away, thankfully. So I divide that out. And that is how you get Snell's law. How many heard of Snell's law? And what this says is that beta 1 times the sine of the incident angle is equal to beta 2 times the sine of the transmitted angle. That's where it comes from. But there's one other thing it says, and I've already spoiled it when I gave it away. You see how the reflected angle and the actual incident angle have to be the same, or that sine function will not be the same? Do y'all see that, class? And this tells us that theta incident is equal to theta reflected, which is nice. So that's Snell's law. You can write that down. Now, we're going to go ahead. Remember, this is just the electric field equated, right? E tan 1 is E tan 2. What else do we know? Here's what I like to do, because I like my life as easy as possible. If that's generally true, it's true at x equals 0, isn't it, class? How many agree? If it's generally true, if you make x equals 0, it's true. Do y'all agree with that? Why did I do that? Anybody? What happens to every one of those exponentials if x is 0? I get e to the 0, which is 1, so that's the reason I do. Whitworth may not do in his book, but I try to make these proofs. So this has to be true as well, right? Strange, it's the same as before when we were doing this for normal incidents. Here's where it gets different. Now, h tan 1 is h tan 2, right? Correct, class? Now, what is the tangent component of the field? If that's z, remember y's out of the board, isn't the tangent component of the h field really the x component? You all see that? If this is region 1 and this is region 2, right? And that's the z-axis, then when I say the tangent component of the h field, it would be the component that is in the x direction. You all follow me on that, class? Show of hands if you do, right? That's tangent. So when I look here, and I'm going to write it down, when I look at this, the incident field's tangent field would be what? It would be this component, right? Sine theta incident, E naught incident over A to 1. You all see that, class? The tangent component of this field would be, did I mess that up? Wait a second. No, this is, sorry, that is, this is the H field. It would be this component right here. I'm sorry. the tangent component here, the reflected field, would also be the x component. You all follow me? As well as the tangent component of a transmitted H field. Now I'm going to equate them, but I'm going to set x equal to 0, z equals 0. That way I get rid of all this crap. All right? It's got to be true always. So it's true for x equals 0, z equals 0, right? And for me to do that, I'm going to write that one over here. Because, actually, where can I write? I'm going to erase those because I'm running out of room and I don't have another board. So what do we get when we do this? The incident H field in the x direction would be E naught incident. Like here we're going to put x equals z equals 0. And I'm looking there and I have E naught incident over a to 1. Forget the exponential. And then I have minus cosine of theta incident ax. Right? So that's the H field from the incident wave. For the reflected wave, I have right here cosine of theta reflected AX or I can get rid of the X component because they're all AX, so it's going to be plus cosine theta reflected right there. And it's going to be times E naught reflected over a to 1 is equal to E naught transmitted over a to 2, right there, times minus cosine of theta transmitted. The only thing I've done is set the x components of the incident and reflected equal to the x component of the transmitted. Y'all follow me on this? I know it's a little messy, but you with me on this, class? Now, I'm going to go ahead and massage these things and get them into a place where we can solve them. Now, I can do two things. Here's what I can do. If I'm looking at the ratio of E naught incident over E naught reflected, you see how I can take E naught transmitted and replace it by these two? Follow me? E naught transmitted is just reflected plus incidence. Can put it in there. Then I can massage it. I've got about 3 minutes to do this. When I do this, here's what you get. I'll try to do it right here. I'm going to have E naught incident right here over a to 1. And that's going to be minus cosine of theta incident right there. Plus, and I'll call it E naught reflected over a to 1 times cosine of theta reflected is equal to E naught incident plus E naught reflected over a to 2 minus cosine of theta transmitted right there. Y'all follow me? I just stuck it in. And then, since I want the reflection coefficient, I define it as such. This is a reflection coefficient for a TE wave or a perpendicularly polarized wave. That is equal to the ratio of E naught reflected over E naught incident. Now, what I'll do is if I divide everything by E naught incident up here, y'all follow me? You don't have to repeat this and do it. Just understand and appreciate what I'm doing. Y'all follow me? This is what I'm after. I have one equation with two unknowns. I'm looking for the ratio of two things. So if I divide this thing by E naught incident, then this becomes the reflection coefficient. This is 1, and this becomes the reflection coefficient. Right? And then I solve for that reflection coefficient. We're a little low on time here. When you do this, here's what happens. I'll just tell you, can check on this. You remember before, you're always going to have the a to 2 minus a to 1 here, and a to 2 plus a to 1. You know that's going to be there. Has to be there because when you go to 90 degrees, that's what has to happen, right? Then what happens is here, it will be the cosine of theta incident, and this will be the cosine of theta transmitted. Here, this is going to be cosine theta incident, and this is going to be the cosine of theta transmitted. Now, understand that's going to be the transmission coefficient. And he doesn't state this explicitly and break it out the way I'd like, but he does show this on page 364, equation 6.133. And I want to just tell you this, he doesn't do the ratioing like I do. Yeah, he's got this equation. Then he does one other thing. He gets the transmission coefficient. And this is the actual reflection coefficient, the transmission coefficient for a TE wave, or perpendicular polarized, is E naught transmitted over E naught incident. And luckily, it's just 1 plus the reflection coefficient for the perpendicular, or it's 2 eta 2 cosine of theta incident over eta 2 times cosine of theta incident plus eta 1 sine, or cosine of theta transmitted, right? This is in your book. Now, I don't expect you to be able to do these completely, but you have to have an appreciation for this. I'm going to give you some more. The oblique incidence is the same technique that I've done here, only now you reverse the roles of H and E. All of a sudden, or not, I'm sorry, the parallel polarization. Now, all of a sudden, E is going to be polarized in the plane of the board, and H will be perpendicular. I'm going to give you some homework on this. I don't expect you to appreciate everything, but at least have an understanding of what the essentials are. The tangent field values have to be equal on either sides of that boundary. That's the key to this stuff. I'll give you the equations, I'll give you some problems, and we'll see you Wednesday, okay?